So topic for today is memory acquisition, and for the next webinar, because this is a bit longer to deal with. And so first bit of motivation about this. What are we going to looking for? And when you've been with the previous sessions, you know that we are trying to first get to the volatile system state. So everything that might be lost when the system will be shut down or cut from power. So the first thing is the running processes. Stefan has talked about this in the last webinar. Like we would know the path the programs are launched from, the command line arguments, because this already might tell us a thing or two if this is malicious or if this is doing something special. Then, of course, we might be interested in the program code, be it scripts or binary executables, because this might be the code of the malware or the exploits, if we are lucky. The internal state, of course, of the system, like keys, passwords, Kerberos tickets, alias active domain credentials, etc., etc. Then there is also the list of open files, and especially the open sockets and network connections, because with them associated are IP addresses, and maybe that's are traces that gives us some hint to where the attacks might come from or where they get their command and control instructions from. If we suspect that the kernel might be compromised, we would like what kernel it is, what version, what the kernel binary is, what modules or drivers have been loaded. And when we dig deeper into the kernel to examine for potential compromises and rootkits there, we might look at the system call table, the interrupt table, or if we are just going after a malicious machine, we might need the disk encryption keys that are stored in the kernel and stuff like that. Name caches are also a nice source of information, although very short-lived. DNS, especially passive DNS, is something we know about. Network information service, the old yellow pages, I think they have almost gone now. They are still maybe in use in some installations. NetBIOS, also if you have some old Windows installations still running in your network. The currently logged on users, and also there are temporary file systems that are mounted into the system RAM, and the contents of these file systems will be lost on shutdown or reboot. So we might want to get at them too. So how do we get this volatile system? Well, in the naive way, it's easy. We run PS, we run LSOF, socketstat or netstat if you have older Unix machines, lsmod, you name, date, uptime, and save the results somewhere for later analysis. So somewhere means not on the local disk or memory, because then we would write to that local disk and we would later like to examine that disk. So we don't want to change the state there. So it's better to put this on some additional attached storage like a USB stick or a mobile hard disk, or we can save this through the network to another machine through the use of netcat, cryptcat, socat, SSH, or whatever we do. So in many live response tools that you see around do just that. They run these programs or the corresponding API calls, and that's what they do for live response. Maybe they do some more, maybe not. That depends on the tool. So the thing is, what about rootkits? The primary purpose of a rootkit is to hide the intruder's presence and its activities on the system. So regarding the intruder's processes, files, network connections, this will not be shown in listings from PS or LS or socketstat or whatever we use. There are two kinds of rootkits, broadly speaking, user space and kernel space. The user space rootkits replace system commands or shared libraries or DLLs when you are on Windows, or they inject their malicious code directly into userland processes. Kernel space rootkits are a bit more complicated. They usually manipulate the interrupt table or the interrupt handler code, or they do it with the system call table or system call code. Or in the case of so-called direct kernel manipulation rootkits, they directly tamper with kernel data structures like the process table so as not to be shown on a process listing. So, and as I've said in the first webinar, we want to put as little trust as possible in a compromised system because we can't trust it. When there is a rootkit, it will be lying to us or hiding stuff from us. So we need to bypass a potentially present rootkit on the system. For the user space, this is a long-established practice. We use clean tools from a trustworthy source. This is the red part here, a green part here, and we put them on a read-only medium. That can be a USB stick with a hardware read-only switch, or in the old days we used a CD or DVD with tools on it. When we were lucky, we could use statically linked tools, but this is getting more and more complicated to build. So most of the time we are now adding clean libraries to the medium and have the search path use the medium only. So that's for the user space, and that worked fairly well until the early 2000s when kernel rootkits were getting more and more widespread. So in the kernel space, when we go to the data structures down here in memory, we have to bypass as much of the system call chain as possible. But on the other hand, it's not entirely possible because all our tools will have to use the soft interrupts and go through the interrupt table lookup and the system call table lookup and the dispatching here. So most of the time we try not to use the process management or network stack subsystems or the virtual file system, and just take the virtual memory management, because that's an area that is rarely tampered by rootkits. And then we will, when we have access to the kernel data structures, we will check them very carefully if they've been manipulated. There are a number of ways to do this, but this is not topic of today. This is not perfect, but that is as little trust as we can put into a compromised system. So we have to use some infrastructure of it as long as we do live response. So how can we do this? One way to do this would be a kernel debugger. This is a very powerful way, but it requires a lot of preparation and especially a lot of internal knowledge about the kernel data structures and how to use a debugger. This is something that is rarely present in most system administrators today. And the other way is to copy the memory contents and analyze them later on another system. Again, there are two ways we can do this by hardware. There are PCI or PCI extended cards that can directly access the memory, mostly through the direct memory access controllers and the I/O MMU. Or you may have heard of this, you can use the Firewire interface, or if you're a newer machine, the Thunderbolt interface. USB 4 will have this functionality built in. And you could also have heard about extracting the memory banks directly from the system by freezing them, literally. But this is quite error prone and will not give you a forensically sound image. It's a good way to work with when you're just hunting for a disk key or something like this, or credentials. Then you might work with even a slightly damaged key, because you can use this as a base for some dictionary attack or some fuzzing. So what we are concentrating on the remainder of this webinar and the next webinar is the software way, which means we are copying from a dev-mem or device physical memory. If you're on the Windows, we can use crash dumps. We can use the hypervisors to copy the guest virtual machines memory, or we can have a look into swap or hibernation partitions or files. So let's give a short intro into virtual memory. I will not do a complete introduction here. That would take way too long. And there are plenty of good introductions on YouTube. So what virtual memory is about, you might have already heard about this, is we make it appear as if every process on the system has the whole memory for itself. So we don't need to care about overwriting other processes' data or even the kernel data. And each process, and the kernel 2 has basically one large linear address space that is broken up into chunks called pages. There are also bigger chunks called segments, but we gloss over this here. And even better, virtual memory will make it appear as if all of these address space is actually available to us, even if this means that it would be a lot more than physically installed RAM. So with a 64-bit address space, this would be billions of gigabytes, and at best, we have a couple of hundred gigabytes installed in our systems. So the basic idea is everything not kept in random access memory. The main memory of the system has a copy on disk. So it's either in the file system for programs and shared libraries or memory mapped files, or it's somewhere on the swap space. So, and when the CPU tries to access a virtual address, it goes through the mapping of an MMU, and either it will translate this to a page in RAM, so it gives the proper physical address here, or it runs into a page fault if the system page is not in RAM, and which will then later trigger a routine that loads this page from disk into the system RAM. There's also some more activity going on, swapping old unused pages, and virtual memory management is a quite complicated system, as I will show you on the next slide, because the translation of the virtual address is a quite involved process. You can think of this basically as being translated into a virtual page number and an offset into that page. And that virtual page number goes through a multi-stage directory lookup. Usually there's one base register. This can be 2-level, 3-level. Modern systems today may have 4 levels of page table or page table directories. And each index here goes into a page table, which gives you an index into the next page table, and so on, until we finally end up at a physical page and our offset here. So this is done through the aid of a hardware unit called the Memory Management Unit, MMU, and who does all these page table lookups in hardware. And even that would take quite a bit of CPU cycles. So there's another hardware support unit called the Translation Look Aside Buffer, which is basically a cache of what the MMU has in information to speed up the page table lookups. And then there's also the matter of hardware caches in the CPU, but this is taken care of by the hardware. We don't have to worry about this here. So what does it mean for memory analysis, especially if we're doing this offline? The addresses meaning the pointers we see in the memory dump, are virtual addresses, while the offsets we use in the memory dumps are the physical addresses. So during analysis, we have to go back and forth between the two types of addresses. So we have to do the MMU task. Okay, we don't have to do this manually because that would be very, very tedious. The forensic tool usually takes care of this. And it can do so because the page tables will almost always be present in RAM. I haven't heard of virtual memory management systems that swap out page tables. I think there are a few around this, but it's usually much more convenient to keep them in RAM. So otherwise, if we don't have the page tables, we can't do the translation. But again, we don't have to worry much about this. So that's a short excursus on virtual memory. Now let's get into the main memory dumps. So if we do this on Linux or even on Windows, the basic approach used to be we just do a copy of def mem or def physical memory, device physical memory, pipe this through netcat on a target host, and that's it. If we do this today on Linux, it will start and fail after about 1 megabyte. If config defmem is not set, it will fail after 1 gigabyte. So that's not enough for a forensic analysis. So this, yeah, I've said this is done on newer Windows or Linux versions, but new means everything since 2003 or so. So that means Vista and on has this limit, and even Linux are from about this time. So you might have a look into your config file and see if config defmem is set. That means it has device memory, and it usually also sets strict defmem and IO strict defmem, so we can access defmem in this naive way. So what forensic tools now do is they use a special kernel module or kernel driver to access defmem from kernel space. So what do? When we do memory imaging, we first need to build usually a profile if our forensic tool needs one. And when we are talking about open source memory forensic, we will talking about the Volatility toolkit. They do need profiles. Then we need to compile the collection tool, meaning the kernel module, and then we can collect the image and do a checksum over it to have the chain of custody asserted. So what do we mean with profiles? Well, we need some additional information, because without any information like that, we have no idea what kind of data is at a given memory address. Is it an integer? Is it a float? Is it a string? Is it part of a structure? We would have no idea. And worst of all, we would have no idea what this structure or string or integer is used for. Is it part of a process control block? Is it part of a file? Is it part of a directory entry or whatever? So what we basically need is the symbol table from the compiler. Kernel debuggers can use that directly if we install the debugging information. That's mostly an additional packet that you can download from your vendor. And but some other forensic tools build a more abstract, condensed structure from this. And in volatility terminology, volatility 2 that is, this is called a profile. So let's go into a live demo. So I switch here and go into another screen. I hope that's the right one. So you should all see a little red prompt here.
Yes.
Okay. So when we download the profile, first good change to check is your kernel version. So here it's 4.12. And the basic thing when you build volatility profile, please do follow this kernel version to the letter and even to the last letter, because you will get gibberish or volatility will stop working at all if you don't really get this as an exact match. So then we need to download and clone volatility. Okay, I'm not showing you how to do a git clone. Can show you where this comes from. So that's the download link for volatility. And then we go into volatility tools. Stop. Here on Linux. And we see a short module here. So we can just issue a make. We need the kernel sources to do this. On Linux, this is just a very, very small module called module.dwarf. And it's linked with it. And we just have to zip up this file and build a zip file, module dwarf, and then boot system.map. And if you want to do this correctly without typing too much, so we have two things added here, and this profile.zip needs to be copied to your analysis machine where you put this into the volatility plugin directory. It's volatility plugins overlays Linux. I will copy this here. So this is basically preparation work. This can be done in advance. Unfortunately, every time we update our kernel, we have to repeat that process. I think the Debian folks have now put this onto a DKMS profile, so you can automatically recompile that module when you update your kernel. So for volatility 3, the thing is a bit different. They use a tool called dwarf to JSON. Again, you clone that tool, do a go build, and then have this dwarf to JSON tool. And with it, you can use this to build a JSON profile. I think they don't call it a profile anymore. So it's only needed for Linux and Mac. Windows has Windows profiles are always shipped with volatility. So, and when we build this from the system map, for example, I think that was this one. So, and this is actually just a JSON file that contains the information needed for volatility 3. Okay, so that's the part of the profiles. Now let's go into the task of actually doing a memory dump. The tool we use on Linux is called Lime, or Linux Memory Extractor. And again, we can clone this from a GitHub repository. Here's the URL. And then we go into source. And as we can see, we can put in a make, and then we have a Lime module. This is the one here. You've seen I've done this previously for a different thread. Again, we have to put away this kernel module on a clean disk so that the attacker cannot tamper with it. And for now, that's all we need to do. So the next part in actually installing, okay, it's there, means we can actually dump some memory. So and this is as easy as doing an insmod of the proper kernel module. And then we put in a path where we would like to put the disk. As I've said, this should be done that's not here. Okay, let's use temp for this. So it has its own format, which is called Lime. And for the minimum, this is what we can do here. And let me see if so you can see it's growing here. It will be something like 8 gigabytes. If we want to know if it's really doing what we suspect it to do, Lime files have a particular signature. So as you can see, that is Lime in reverse. So we can be sure that it's actually dumping some memory here. Well, I will interrupt this here. Come on. Well, this can take some time now. Well, it's almost finished. I think it's done. So we can also use this to write it away over the network, which means we just use a slightly different way for the path here. In this case, the path is called TCP and a port number, let's say 12345. And then we can start the dump. And as you can see, it doesn't automatically unload the Lime module. So we have to unload the module first. If we do this multiple times, like when we are practicing this, don't forget to unload the module. So what we have here is an open port on the machine. As you can see here, there it is. The port we've just opened. Awesome. So, and if we do a netcat on this doesn't want to. So, and it then goes and writes away. Again, I will stop this here. And you can see it's already here. let's free a bit space here. So another way to do this would probably be using SSH. While we're doing the memory dump. So again, we put this here, and then we'll have the so then we open another session here. Makes this a bit more readable. Okay, so I think you get the idea. Let's stop this here. So. Come on, so. Okay. So this is basically what we like to do. Two more things when you do the dumping thing. There are two more parameters. I'll just give you here on the command line. One parameter is called compress, so we can compress the image. And we also have the idea to do the checksumming right away with the image in form of the digest parameter. So again, I think you get the basic idea how this will work. In this case, it will open up a second connection, which is probably not what we really like to do here. So So we let this dump away and go back to the slides. So as I see here, I've put this all in the slide decks. Again, here, my warning and advice not to put this here. Here's the way how to do this with Netcat and SSH. So checking the image, as I've said, this is used to assert the chain of custody, so that we can say for sure that the image has not been tampered with since acquisition. So we can use the built-in hash sum features of the collection tool, which is usually nice. It's a bit faster, and it's one less thing we have to forget. And but keep care that we should probably not be using broken hash algorithms like MD5 or SHA-1. You still see them a lot in the literature, and some forensic tools do not support anything newer. So SHA-256 is okay for now, but again, the recommendations are not to use this as a long-term solution. So SHA-512 or so is even better, or SHA-3. Organizationally, this means we should use the 4 eyes principle when collecting the memory, which means that another person should be present there, so you have a witness, and we store and transfer the checksum apart from the image. So if we would store it alongside the image, it would be trivial to tamper this. So if we can access the image, we can also give it the new checksum. So store them at a separate location, or even better, use cryptographic signatures like from PGP or S-MIME. It's your choice. But I think this hasn't yet made its way into law enforcement. So again, when you verify the checksums, one word of warning: when we use the built-in checksum features, the checksum is that of an uncompressed image before the compression, at least with Lime. And when we use external tools, so we first take the image and then do the checksum, we have to first uncompress the image and then take the checksum, or otherwise it wouldn't match. By the way, Lime uses a bit peculiar compression algorithm called kexec, but this tool is available, I think, on practically every Linux distribution. So a bit more on this. Windows does this in a very similar way. The tool here is called WinPmem from the Pmem suite, which also includes tools for Linux and Mac, but they're now in some sort of transition period. So the only tool I've seen that is really ready for use is the WinPmem mini driver, and we can use a CERT util or the PowerShell to do the checksumming. So that's about memory dumps. Now about crash dumps. As I've said, there are a number of debugging tools in today's kernels. In Linux, we have some framework around printk to do this. We have tracing frameworks like dtrace, or I don't know what it was called on Solaris. Many operating systems have this sort of tracing framework, which is nice when we use sandboxes for analyzing malware. But for most of the time, we use a kernel debugger. And we can also use this to do live kernel debugging. So we can analyze a running system through an attached debugger. Attached means it's usually through the serial console. Even on an embedded system, there's a way to have something like that. It's called the JTAG interface. Or we have something like network consoles. In Linux, it's a kernel module which is called kgdb over Ethernet. There's also a module called kgdb over serial, or kgdb over console, right? kgdb OC is called there. And the debuggers we can attach is kdb or kgdb, or on Windows, the kernel debugger or Windows debugger. So that's one way: live kernel debugging or post-mortem debugging through the use of a crash dumps, which can then be imported into forensic tools, for example, volatility. So the advantage of a crash dump is that we can also analyze the file with debuggers. The memory state usually doesn't change when the dump takes place, which is not the case with the volatility Lime or Pmem. And crash dumping is present on practically every operating system you will encounter. So on the other hand, it also requires preparation of the OS. We need to configure the crash dumps, especially to include a full memory image. And this configuration usually requires a reboot to take effect. Or also triggering a crash dump will usually trigger a reboot after the dump has taken place. live dumps may not usually do that. So on Linux, this is an involved process. I can only give you the very basics. What we need is the kdump and kexec packages, which are distribution dependent. Then the production kernel needs several options enabled, like config kaccess, crash dump, proc VM core, and the sysfs. The later two ones are probably always set to yes. And then we have to give this kernel a boot parameter, which is called the crash kernel. And with xxxm, meaning we have a number of megabytes in kernel memory reserved for something called a crash kernel. Linux has a mechanism called kexec, which can be used to execute a new image without going through the reboot and BIOS initialization process. This mechanism is called kexec. So what we really do when we take a crash dump is we execute a crash kernel, and this crash kernel takes the old kernel and its memory image and dumps it to disk or over the network. The configuration is in etc's sysconfig kdump, at least on SUSE and Red Hat-based systems. Debians and others may also use kdump.conf. There's also a service which needs to be enabled either through the initd scripts or system control. And then all we need to do when we have done the preparation is to signal the kernel to crash and hand over control to the crash kernel. So on Linux, we can do this or have to do this with an actual root login. Using su or sudo won't do. We have to use real user ID equal to the effective user ID, and both being 0. So, and if we can still trigger the sys requests, we can activate that mechanism and then use this little line to do this. We can also hit the, I think it's Alt sys control and then C, or Control sys control C, and do this on a keyboard. But over the network, we may not always have this opportunity. So we can use this here through the proc file system. The dump file can also be written over the network through SSH or NFS. So a live kernel dump can be done through a copy from proc kcore. This is a file that should be present on your system. And it's basically a copy of the system's memory wrapped in an ELF core dump format. So we can analyze it with a standard debugger. When you see that file, you may be surprised because it's huge. It's a couple of terabytes in size. So you can see here, it's really, really huge. So I think here it says it's 128 terabytes, which I think is the current maximum address space size on 64-bit Intel systems. It's not quite 64-bit. I think it's 43 out of the 64 bits. Again, back to slides. So there are two tools to do this. We have get kcore from the volatility toolkit. It's in the tools Linux kcore directory, or the kcore dump tool from a guy nicknamed Schlafwandler. And this version is supposed to work with address space randomization from kernel 4.8 onwards. But I've tried get kcore when I prepared these slides, and it worked just well. So maybe the volatility guys have updated their tool. But again, don't forget the debugging symbols to include in your or put alongside your core dump because you will later need them, or your volatility profiles. So on Windows 10 and even Windows 11, it also means we have to enable the dump settings, which mostly means we have to set this thing, the system, to do a full or complete memory dump under writing debugging information. So that's this screen we were talking about. This is under Advanced System Setting, the Advanced tab here, and then you go here and have the file location and the type of the dump you will be doing this. Or you can do this through the Windows Management Instrumentarium from a script console like PowerShell or Windows Command. So, and if we want to initiate a crash dump from a keyboard, we have to create some registry keys depending on our keyboard type, PS2 keyboard, USB keyboard, or even a virtual keyboard on Hyper-V systems. It's always the same key, it's only residing in different parts of the registry. So, and when we've done all this preparation, we can use the right control key, and by right I mean literally the right one, right of your spacebar. Hold that down and press scroll lock twice. The scroll lock key is usually the one right beside your sys request key. We can change this key. There's an explanation how to do this on docsmicrosoft.com. An alternative would be to use the system call sysinternals tool. They have a nice tool called Not My Fault, which we can call from a command line interface and give it the parameter crash and an integer for the reason to do so. Like 0x01 would just be good enough. The tool comes in different flavors. The 64-bit ones are named 64, and if they have a C attached, these are the command line versions. The GUI versions don't have the C attached. So when you download the suite, you actually have 4 Not My Fault tools, one each for 32 and 64-bit OS, and one each for console and GUI. So, and if we want to do a live kernel dump, we can use, we have to install the Windows debugging symbols. We can get them from the Windows SDK. They are available for free from Microsoft. And then install the live KD tool from sysinternals, which will just call the kernel debugger you see here. And when you issue here the dump command, .dump command with /f, which means a full dump, and then give this the path of where you want to put the dump. Again, it's best to do this on a additionally attached storage here, or maybe even a Systes share. So we are coming to the end of this. When you are looking for a memory collection tool, there are quite a number of tools around this. I've shown you open source tools. There are a lot of very old tools which aren't maintained for some 10 years or so. So I haven't included them here. And there's also a number of commercial tools like FTK Imager or Kome, Dump It, and many other more. Unfortunately, every comparison I've seen is also nearing 10 years of age. So when you want to select one tool, I suggest you do some comparison and ranking by yourself. So operating system and hardware architecture support are one thing you will consider. So especially if you're having systems running on ARM or PowerPC or whatever else you have on CPU architectures. and have a look in how well the tool works in adversarial conditions. So like there's some rootkits or some anti-forensics presence. This would be come to mind first, but also, especially on Windows and Mac, there might be some DRM or copy protection software which doesn't like memory being copied. And of course, there may be faulty memory banks which may throw our tool off balance here. And you may also have a look into past bugs and vulnerabilities. So then there's a question of if you prefer a GUI tool or want something that can be scripted, want something that can be put on a USB stick or mobile hard disk. Not every tool supports a standalone configuration. Some of them want a full installation, which is, from my point of view, not the best way to do, because that would alter system state too much for my taste. But again, your mileage may vary here. Then the type of images that are supported. Is it a raw file? It's Lime, it's crash dump file, whatever else you have. There's the matter of compression, and if we have a proper uncompressing pressing tool on our analysis machine. If our file system doesn't support very large files, so meaning larger than 2 or 4 gigabytes, we might have to split the image over multiple files. So we have to see if our tool can support this. And there's also the way of writing away the dump over the network. And then there is the question of how much memory does the tool take for itself, because that's memory that's overwritten in the RAM. This is also altering a bit of a system state, but again, this is unavoidable, but a smaller tool would probably be having less impact on the system state. And last not least is performance. So how long does it take to capture the memory image? As a small tip, when you write away over the network, you should opt to use compression. Saves you a lot of bandwidth and time. So there are many ways to get to a system's memory. I will cover a couple of more in the next session. Most will require some preparation, and if you are going into PCI cards, you will have to install some hardware beforehand. Kernel debugging is hard, although very powerful. A folk here from Germany called Andreas Schuster has done a lot of research in the area of live kernel debugging on Windows, although I'm not sure how much of this is still applicable to Windows 10 and Windows 11. And the state-of-the-art way to do memory dumping today is through a special kernel module or driver. This is mostly generic with regards to requirement, but it also needs some preparation, but that can be done offline on a clean machine. Crash dumps can be an alternative if you have enough space on the disk for a crash dump and have configured your kernel for this. You might have actually done this if you want to set up your kernels for some debugging. So this can be an alternative, as these crash dumps can be used both with kernel debuggers and forensic tools. So, and in the next session, I will be talking about dumping memory from virtual machine hosts and have a look into swap and hibernation files. So, being that, let me thank you for your attention, and I'm still available for a few questions if you don't mind spending a bit of time with me even after the hour is full.